Hello, and this is Charlie, and we're going to go ahead and get started with the heating section right now. I'm only going to be covering the, how we create fire, how we move fire, and forced air furnaces. It's just too long to be getting into hydronic, steam, and everything else. So I am going to go ahead and do that in another session, probably in a couple weeks. Okay. So the first thing we should be talking about is, again, definitions. It seems like I always want to start there. BTU, British Thermal Unit. You are expected to know what that acronym means. You're also expected to know the definition of it. All right. And down on the bottom there, 1 BTU is the amount of heat required to raise 1 pound of water 1 degree Fahrenheit. So those are going to be the two magic numbers that we're going to want to remember. 1 pound of water and 1 degree Fahrenheit. Now, when they talk about the amount of energy, what they're really talking about is how much fuel am I going to be using in order to raise that 1 pound of water 1 degree Fahrenheit. So whether that fuel is natural gas, propane, electric, wood, oil. Now, we don't have the ability to measure the amount of wood that we use other than tossing a log on something. And same thing kind of goes with any other hard fuel like pellets or coal. Even oil is kind of limited on how much it goes through. But with natural gas, which most of the Chicagoland area here we have, we actually have the ability to measure how much gas gets used to create the fire. We can convert that amount of gas that's being used into BTUs. So on my website, thehomeinspectors.com, and then if you go under education and employment there, you're going to find a link to a gas timing chart on there. And basically it measures in seconds how many times it takes one of those dials to spin around, whether it's half pound, full pound, whatever. And each one, however many seconds it takes to do one full revolution, correlates to how many BTUs are being used of natural gas. So what's nice about that, if you want to go a little extra or a little overboard, you can look at a 80,000 BTU furnace, for example. And I don't have the numbers memorized, but let's say it takes 60 seconds to go through a 1 pound or a 2 foot-pound circle. We could go ahead, and if we know that the furnace label says it's 80,000 BTUs, we could run that timing chart, and as long as it matches up, we're good. If it goes too fast, we're burning too much. If it goes too slow, we're burning too little. But nonetheless, I'd like you to commit this to memory. This is something that we're going to be using throughout today. We use it on air conditioning. Basically, anytime we want to take heat or absorb heat or discharge heat, we're going to be referring to those as BTUs. All right. Next thing is going to be the fire triangle. And some people refer to this as the fire tetrahedron as well. These are the three things that we need to go ahead and make a fire. So number one is fuel, whether that be wood, gas, propane, oil, whatever it may be. We need some sort of fuel that we can burn. We do need to mix that with oxygen. Everything has what we call a flammable limit. So there's a lower flammable limit and an upper flammable limit. In other words, if I had natural gas and I was in 100% gas environment and I didn't have any fresh air in there at all, and I was starting to put sparks inside that gas, it would not ignite because I need to have that oxygen. I have to have the right mixture. I have to be between the lower flammable limit and the upper flammable limit. And then some sort of an ignition source. The fourth one, which is that tetrahedron, is the chemical chain reaction that happens and mixes all three of these things together. All right. Another term I'd like you to remember is something called complete combustion. Now, we really don't have this complete combustion. It doesn't really exist. But if we used 100% of the fuel mixed in with the oxygen, we're not going to have any byproducts at all from the fire. Usually when the first byproducts, or when we don't get a complete burn, and we usually don't get a complete burn, we're going to start getting some byproducts that comes out of there. So carbon monoxide is going to be our number one byproduct that we're going to be measuring for, or we may choose to measure for. We do put carbon monoxide alarms inside of our residential buildings. And I think that's important enough to say that in the state of Illinois here, we do have a carbon monoxide law. So we should be having a carbon monoxide alarm within 15 feet of every bedroom. All right. So if we start limiting the oxygen that we have in there, that's the more incomplete burn that we have. The more incomplete the burn is, the higher the carbon monoxide levels. If you start thinking about campfires, we get a very incomplete burn, and so much so that we are producing large amounts of carbon monoxide. It doesn't harm anyone because we're outside, but we're actually getting to the point where we're producing smoke as well. So fuel, heat, oxygen, I would like you to throw in there the chain reaction, but those are the three main things. So fire triangle is the fuel, heat, and oxygen. Tetrahedron, we're going to add the chain reaction to it. So the next few slides are, just more designed to be somewhat humorous, but also a little bit of an eye-opener, all right? Now, again, we're going to have oxygen and the fuel. In this drawing or illustration here, the wood that we're creating the fire, that's our fuel. The fresh air is the oxygen. Now, the radiant heat is moving the air upwards, or I should say the heat is moving it upwards through convection, which is going to actually cause a cold air to come in from underneath. That cold air coming underneath is going to be our combustion air. We do need to remember that word combustion air as well. So when the fire is radiating off, and we're going back to the caveman inventing fire stuff, forgive me for digressing so much, but he's warm in the front of him. And because there's kind of a cold draft that's coming in to go ahead and feed that fire with oxygen, his back is actually going to be cold when it comes in there. So the caveman ends up getting a little bit smart, or sort of smart, and he takes that fire and he starts putting it inside. All right. So granted, it's inside, but it does a few other things too. So we're getting our oxygen in through the openings so we could still make the fire. If we lose the oxygen, well, obviously we need oxygen to breathe, so he's not going to be living too much longer. But more so, we have the fire is going to radiate off the walls and then bounce back, and this way it keeps the front and the back of him open. The front and back of him warm. However, with the smoke and everything else that's there, we're afraid that we're going to asphyxiate this poor guy, so we don't want to leave it at that. So we take the next step and we go back to the Indians. All right, they went ahead and put fire inside of the teepees to stay warm in the winters, and they actually did well with this. The trick with the teepees, though, they were actually open on the bottom so that fresh air could come in through the bottom. The heat would then radiate and hit the sidewalls of the teepee, come back to the person. We had it open on the top so the bad gases can come out, and we don't asphyxiate anyone, and we keep getting fresh air coming into the teepee to keep them warm. Then all of a sudden we start bringing these in the houses, and we do the same thing. Typically they were with fireplaces. Now we're getting into the modern day heating systems that we have right now. We take a fire, we put it inside of a metal box, maybe a wood stove or something like that, or like I said, a fireplace. That wood stove, the metal around the wood stove gets really hot. That radiant heat bounces off and goes ahead and heats up the walls of the house, which in turn reflect that heat and keep us warm on both the front and the back on both sides. We still have a lot of waste byproducts from the fire, so we need to kind of channel that away. And we finally evolved to the point where we're putting chimneys and flues, and we're directing all that bad gases out of the house. All right. So if we break it down to the bare bones minimum and we take this wood stove, in all reality, this is what we would refer to as our heat exchanger. All right. So I have a fire inside the wood stove or inside that heat exchanger. That fire gets the metal of the wood stove or the metal of the heat exchanger extremely hot. That heat now is going to start heating up the fresh air, the clean air that I breathe. We're going to separate the bad gases and the bad fires and the byproducts. We're going to separate that from the air that we breathe. And then that bad air is going to be exhausted out through the chimney or through the roof of the house. 3 more words. If you don't know what these are, I suggest you write them down. We are going to be using them again. So these are the 3 different ways that we move heat from one location to another. As we mentioned earlier with that wood stove, radiation, that heat is going to basically be going in a straight line. It's, I like using the sun as radiating heat as a good example, because we can all relate to when I'm out in the sun, I feel it hitting me, I'm nice and warm, I'm actually feeling like I'm getting a suntan, or obviously me, I never tan, but that's beside the point. But yet if I walk into the shade and I get out of the beams of the sun, I start to cool down because it's not directly hitting me anymore. So with radiation, I can actually block that heat just by putting a wall or a barrier between one object and another. So it goes in a straight line. It will reflect off of things. It will bounce off of things. But mostly it goes in a straight line. Convection, anytime we move heat through water or air, we're going to be calling it convection. So in furnaces, we have ductwork. We heat up the heat exchanger. We blow our circulation air around the heat exchanger. We absorb that heat. The fan blows it through the ductwork into the rooms where we want that heat. That's moved through convection. Hydronic heating systems. We use water. So we heat up the water. We pump the water to another radiator, another location. We move the heat from point A to point B through water, hence convection. Conduction is going through a solid. Just the fact of having the heat exchanger with the fire on the inside, the heat exchanger or the heat transferring from inside the heat exchanger to outside the heat exchanger, that's a solid material of metal, and so we're going to call that conduction. Every time I see this slide, I always go back to the Home Alone movie where you put that little heating element on the door handle and Joe Pesci touched it on the other side and burned his hand, and again, I just keep thinking conduction. Move it from the inside of the house to the outside, whatever. It was funny then, but obviously I'm not any humorist. So gas heats will be the next thing that we come up with. And I'm going to talk about gas, propane, and oil before we get on into the furnaces. All right, so here's a typical gas meter coming into the house. And not all areas have this. Here in the Midwest, it's very common that we use natural gas. I know there's a lot of areas that use propane. We still do have fuel oil in our area. I still see those trucks driving around, and I run into old tanks, even though they're abandoned and left alone. But we do run into old tanks and crawl spaces and so forth. But we'll get to that in a little bit. So as the gas comes in, one thing about natural gas in our area anyway, it's pretty clean. They do a good job baking out any humidity, they being the gas company. They get rid of the humidity, they kind of heat up the gas and get it nice and clean and dry. It gets filtered as it comes through the systems. For the most part, gas is kind of run at pretty low pressures, at least in residential areas. If you start getting into commercial areas or where the big main feeders start going before they disperse and downsize down. I remember when I was on the fire department up on Lake Cook Road, we had an open gas pipe that was leaking, and that had to be like a 50 to 100 pounder. I've never heard such a loud noise and gas spewing out of there like there was no tomorrow. We actually had to zone off a big area before the gas company came there to shut everything down so we can make it safe again. But usually with residentials, we're going to be coming into a residential neighborhood somewhere around 4 psi, plus or minus. So that pipe, this one right here, oops, sorry about that. So this pipe right here as it comes in, this is where the gas comes into the house. All right. And as it goes up the line here, this is going to be our shutoff valve or our isolation valve for the house. We do have to document in our home inspection reports the location of the main shutoff of the gas lines. That's actually in our SOP through the state of Illinois. So we come up here, it's typically 4 psi, and we're going to come into our regulator. This regulator is going to lower the gas pressure down to, I believe it's 1/4 of 1 psi. And on the bottom here, you're going to see a little opening, and typically there's going to be a screen under there too. That's a pressure relief valve. So if for some reason that there's a surge of gas pressure that comes into this gas meter or towards this house, instead of pushing that gas pressure into the house, what we're going to do is discharge the gas to the outside. I have personally never seen and I should back this up a little bit, I've never seen doing a home inspection or in my own home where we were spewing gas coming out of there. Now, in my neighborhood or when I sit on the porch, every now and then I'll get a whiff of gas. I don't know if it comes from our house or the neighbors. I can't seem to source it down. Every time I get the gas detector out when we smell it, whatever happened, it stopped. All right. Going back to the fire department, though, I have seen where these things have failed, especially on commercial properties. They open up and they stay open, and it just starts spewing gas out of there. Now, obviously, that's going to be a problem. So we come back in, 4 psi, the pressure reducing or the regulator will lower it down to 1/4 of 1 psi. Then it comes to our gas meter. These dials on the gas meter is what I was talking about. You time as those go around when you do the gas timing chart. And again, you can find that up on our website. And then it comes up through here and then into the house and comes forth. So what belongs to the gas company and what belongs to the homeowner, you could see up here is kind of the last part that was painted, this universal fitting. So everything to the right of that that's not painted, that belongs to the homeowner. The gas meter regulator pipes that go down into the earth, that belongs to the gas company. Now, this pipe that we have above ground will be metal, all right? But this metal pipe goes into the earth maybe a foot, maybe 2 feet. It doesn't go far. Most of the gas pipes that we have underground are all going to be plastic, all right? One of the questions I like to ask people when they start in this business is, should we ground our electrical system to the gas pipes? A lot of people look at me like, what, are you crazy? No, because if there's a spark, it's going to explode. That's not the right answer, all right? We shouldn't, again, if we have 100% natural gas, it's not going to explode, even if I start getting sparks to it. If I have a leak, that's a problem, and any spark nearby that leak can create it, but a grounding isn't going to do that. The main reason why we don't ground at the gas pipe is because it's plastic. I don't get a good connection to the earth. All right. The last thing is going to be this tracing wire, this yellow wire that wraps around the pipe here. All right. I'm sure we've all heard of Julie or whatever it's called in your area. Here it's 311. So before you dig, you want to get the joint utilities out there and mark where everything is. So because the gas lines are underground and they're plastic, we can't use a metal detector to find where they're at. So this wire wraps around that plastic gas pipe, so they could put I think it's called a sonde. They could put something where it creates a signal, and then they could run their finder or whatever that's called over the top of that, and they can mark exactly where the gas line is, so that we don't dig into it. All right. So short review. Gas and then comes in through a plastic pipe, switches over to a metal pipe. That wire that goes around it is a tracing wire. Our shutoff valve. We go to our regulator. We usually go from 4 pounds to 1/4 of a psi. And we go ahead and run our meters so we can pay our bills, and then it comes into the house and feeds our gas appliances that we have inside the homes. All right. So as it comes in, just a few more terms. When I have a whole bunch of pipes together, we call that a manifold. Whether it be inside of a furnace, a water heater, whatever the case is, it's just referred to as a manifold. Anything that goes down is a drop. Anything that goes up is a riser. Anything that goes down at the bottom of the drop, we're going to want to put a drip leg or a sediment trap in there. All right. One of the nice things about doing these home inspection classes and the live, I get to meet a lot of people that have a stronger expertise than I do in many different fields. And just recently, we had a natural gas guy coming out there, and because for me the drip leg, I always thought of it was, when we use pipe dope to put all these pipes together, we're going to get a little bit of garbage, a little bit of debris, and I want to give that a place to land so that it doesn't come in and clog up or ruin my gas valve. All right. But he was explaining to me that they do have some issues where moisture and water gets in there, and you have to have that drip leg because sometimes they got stuck where the gas valves were in the open position and they couldn't shut down because of rust and corrosion that was there. That made a lot of sense to me, and it put a lot more importance to the fact of having a drip leg in there. All right. But mostly it's just to catch the garbage. I don't know anybody other than this gentleman who gets called when there's problems. So he gets identified, he can go ahead and see these, identify what the problem is, and fix the problem. He's the only one that I ever ran into that actually had to open that up, drain it with the water, and go ahead and close it back up again. So for him, it has happened. But other than him, I've never heard of anybody else doing that. All right. Risers, drops, drip legs, and those are going to be our main things here. Good.